Hello, everybody. Welcome to the seminar series of Disaster Resilience Analytics Center at Wichita State University. Today, we have our speaker, Dr. Omar Sediek, who is a bridge engineer at Alfred Benes and Company. He received his joint PhD in civil engineering and scientific computing from the University of Michigan in Ann Arbor, with specialization in seismic resilience of communities. He received his BS and MS from Cairo University in Egypt. His research interests span from the stability of steel members to community resilience against natural hazards and the use of artificial intelligence in structural engineering. So with that, we welcome, on behalf of DRAC Center, we welcome our speaker.
Thank you. Thank you for the introduction and for hosting me today. So today I'm going to present a collaborative work on distributed computing in natural disaster resilience. So I'm going to present our work, which is SRTI, or Simple Runtime Infrastructure, which is an accessible distributed computing platform for interdisciplinary simulation of natural hazard scenarios. So this work is the output of a larger project by University of Michigan. It's funded by NSF. It's called ICORE, or Interdependencies in Community Resilience. So it was collaboration between professors from different disciplines, civil engineering, computer science, social science, and we had one programmer. And even inside the civil engineering, we had structural, construction management, and different disciplines. And I was part of this as a PhD student. I was involved in the development of the software, the SRTI software that we used, and also in the seismic resilience part of this, which I'm going to present today. So let's start with the motivation behind SRTI. So actually, disaster science involves many disciplines. So as we can see here, we have, for example, power grid analysis, we have building analysis, we have social analysis, economic analysis, healthcare analysis. We have different disciplines in disaster science. And actually, the disciplinary boundaries are high, and each discipline has its own computational models. So social science guys, they have their own computational models. We structural engineers have our own finite element and detailed models. Economic, they have their own CGE and whatever models. And we need to connect all of these models together in order to be able to take all the dimensions in disaster science. But these models were not designed to be connected. So each discipline has a detailed model, but they only focus on their objectives, not connecting these to other disciplines. And from here came the idea of using distributed computing in disaster science. So let's start with the existing distributed simulation frameworks. So actually, distributed simulation decomposes a larger scale system into independent simulators. And each of these simulators can either run on the same machine, or they can run on different machines, but they are connected on either LAN or local network or a wired network. So one of the old ones is the DIS, or the Distributed Interactive Simulation, which is an IEEE standard, and it was developed by US DoD. And the high-level architecture is actually another set of IEEE standards for building distributed simulation tools. But HLA is different from DIS in the idea is that they use a middleware, or they have a central hub where it receives all the input from other simulators and distributes it to the other simulators. And this is called a runtime infrastructure. And from here came the name of SRTI, or Simple Runtime Infrastructure, which I'm going to present today. Another one is the test and training enabling architecture. The TINA is similar to HLA, and it uses also middleware, and it was developed by DoD. And as you can see, all of them are developed by DoD, and since they are not accessible, they are not easy to use, and there are other techniques like LCM and GBB that does the same function. However, all of these simulation tools have some limitations. So here is a comparison between 4 of the available distributed computing tools. For example, as you can see here, the comparison is between being open source, simple message format, has the feature to control the quality of service. Is it a low barrier use? Is it portable? Is it fast? So as you can see here, none of these 4 systems have yes in all the criteria. So that's from here, we decided actually to develop our own tool. So at the beginning, the objective was to build upon any of the available tools. And actually you have one LCM trial of connecting different simulators in natural hazards. But then given that, we decided to go with our simple run time infrastructure tool. So what are the specifications of SRTI? First, it's open source and free to use. It's available on GitHub. It permits distributed simulations across multiple machines, or as I mentioned, on the same machine. It supports different programming languages and operating systems. So now it supports Linux, Windows, and Mac. And also it supports a different programming language. It supports Java, supports C++, MATLAB, and NetLogo. It uses a publish subscribe data transmission pattern that I'm going to elaborate more today. And also it provides a pre-compiled component to be directly downloaded and used without any installation. So it's just a .e, it's an executable file. And the data messages are parsed as strings. So it allows flexible data representation without recompilation. So this was a limitation in LCM. You have to compile each variable different and have to predefine all the variables. But here, everything is converted to JSON format. And actually, it's easy for humans to read and write. You can see the messages going back and forth between the simulators. And it's also easy for machines to parse and generate. And it achieves the extensibility and scalability, as I'm going to show today. So let's start first with using the use of a publish subscribe data transmission pattern. So here is like you can imagine the RTI or the runtime infrastructure as a pipe where each simulator has its own pipe. It publishes the data to its own pipe and then subscribes the data that it wants from other simulators' pipe. So for example, here we have the scenario simulator. So the scenario simulator, for example, if it's an earthquake, it provides the ground motion parameters like peak ground acceleration, spectral acceleration, and so on to the pipe related or the channel related to the scenario simulator. And then comes the seismic simulator, which provides the peak ground acceleration at each location in the community. It subscribes the data related to the scenario, for example, the parameters of the ground motion, and then it publishes the output to another pipe, which is related to the seismic simulator. And for example, if we need to represent the water system in the community, then all what we need is to subscribe the data from the pipe or the channel of the seismic simulator and use these data to evaluate the damage, publish the data to the damage simulator channel, and so on. As you can see here, we can connect as many systems or as many simulators as we want. We have the parse system, we have recovery optimization system, we have visualization. So each of these simulators can be pictured as a black box. I do not need to know what is inside the direct damage simulator or the building damage simulator. It can be as simple as a fragility curve of the power system or as detailed as a finite element model. Me, for example, if I'm a visualization or a human expert, then all what I need is some information about the seismic simulator, the building damage, and so on. So we can add other systems, as I mentioned, just adding the set of simulators, subscribing, publishing, and adding new channels. Again, it permits distributed simulations across multiple machines. So here's an example of a wind analysis simulation. It was actually done at our lab. So as we can see here, we have 5 machines connected to the same network, and each of the simulators is running on a different machine. So now we can distribute even the computational load on different machines or different resources. So again, it achieves extensibility and scalability by adding any new system. So as we can see here, we can add a building system, we can add a transportation system, and so on. So here is an example of a building damage simulator. So the building damage simulator can, as I mentioned, can be as easy as a hazardous model, which is a fragility curve, single degree of freedom, a shear model, plane frame model, 3D model, or a 3D detailed finite element model. All of these are inside the black box that the other simulators does not know anything about it, except for the message or the input they are subscribing to. So let's move through the history of SRTI. So SRTI actually now has 2 versions, version 1 and version 2. Version 1 was actually developed for expert users. So as we can see here, the components are the user simulators, of course. So you have the simulator here and the RTI server. And this RTI server actually has a GUI. It was it's not a user-friendly GUI. And also it has its own API. So you first need to load the RTI library API inside your simulator and then use the functions inside this library to connect your simulator to the RTI server. So again, all of these components, as I mentioned, are pre-compiled, and actually each message is hidden from the user, but it's sent as a JSON object. And actually this version for non-experts was very hard to follow because you had to write a lot of lines or a lot of coding lines to be able to define the message, define which simulator to subscribe to, which channel. So you had to define each component manually. However, as anything that is not user-friendly, it allows more flexibility than the second version, which is version 2. So version 2, it's for general users, but it was tailored for natural disasters. So here, the new or modified components, the RTI server now has a management logic. So it manages when and where to send the message. Before, all the messages in the first version, all the messages were floating inside the channels, and you need to subscribe the right message at the right time. But here, you define which simulator runs to which, before which simulator, and which simulator is subscribed to which message at which time. So all of this is done through a management logic that we developed. And actually, this was the civil engineering part of it. So from the standpoint of a computer scientist, all they need is just define your message. But here we had our input to actually manage the messages. And actually, there is an RTI wrapper that simplifies the process of defining the messages. So all what you need is to define some variables in MATLAB, and the RTI wrapper will do everything for you. And the new thing, which is a more user-friendly SRTI GUI, where you can see the messages going back and forth between the simulators. You can see your simulators, and you can see the different stages of the analysis. So here is the SRTI graphical user interface. So as you can see here on the left, these are the simulators. So the green the green boxes are the simulators. The red boxes are the channels, and a connection between a message and a simulator defines that if it's going inside the simulator, then the simulator is subscribing to the message of this channel. If the message is going from the simulator to the channel, then it's publishing the data. And here are some of the edit tools available in SRTI. And I'm going to show an example in our field, which is the seismic resilience of communities. So this is a generic example. So now let's move to a case study, how to use SRTI in natural disasters. So this is showing the seismic resilience of a power network in Shelby. So as we can see here, this is the studied community. It is Shelby County in Tennessee, and here is the studied earthquake scenario. Here is the power supply infrastructure. It has multiple components related to the substations, related to the transmission lines. And also here is the building. So there is around 290,000 buildings analyzed in this scenario. And here we are considering a hypothetical 7.7 earthquake. So if we look at how is this modeled, so first this scenario simulator provides all the other simulators in the framework with information about the power network. Then the hazard simulator propagates the ground motion to the location of each component in the power network. And then we used the hazardous fragility curves to evaluate the damage. And then the recovery trajectory is evaluated based on hazardous functionality curves. And then there is a visualization simulator where you can see the damage progression during the earthquake, and you can see also the recovery after the earthquake, as I'm going to show shortly. So here is the seismic resilience framework. So as we can see here, this is the SRTI server, or the bunch of pipes or the channels that I showed before. And here are the simulators considered, which the scenario simulator, hazard simulator, network damage, network performance, visualization, network strategy, and network recovery. And as we can see here, the simulators are color-coded to represent different stages of the earthquake. So here we can define 4 stages for the earthquake. Stage 0, it's the initialization. It's the community before any earthquake, just the community. And then we have stage 1, which is during the disaster. So we can imagine any disaster having the same 4 stages. Then we have a stage 2, which is just one stage to compute the losses. It's just one step to compute the losses among the different components of the community. And then a stage 3, which is the recovery stage after the earthquake. So as you can see here, the seismic scenario simulator is just initializing the data about the community and the type of hazard. And then we have stage 1 during the earthquake. The network performance is between stage 2 and stage 1 and stage 3, because it evaluates the network performance during the earthquake and during the recovery as well. So the time step during stage 1 is 0.01 second, but during stage 3 is 1 day. So as you can see here, we have different scales, and SRTI can actually handle these different time scales. So as you can see here, here is the damage during the earthquake itself. As you can see, green means slight damage. And then as you can see, it changes over time. So now let's add another system, which is the building and the human infrastructure. So actually, the first part was done by Dr. Sion. She was part of the lab, and her research was focused only on power networks, the infrastructure networks, gas, power, and water network. And my work was related to the building and human infrastructure and the household behavior. So we combined both simulators by just adding out my simulators to the framework that she developed, or her simulators to the framework that I developed. Till now, I don't know anything about what she's doing, and she does not know what I am doing exactly. We are just sharing the messages. So the same way we added, as you can see here, what we need to do is to add a set of simulators related to the building damage, component damage, casualties, repair cost, repair time, and also the household decision. And in the recovery stage, we need to add a recovery or a building recovery simulator. So the household decision simulator actually utilizes a smart technique which represents the behavior of households after disasters. And here, the household decision actually is one of three: either to demolish and rebuild the building, or repair the house, or just leave the community. And it depends on many structural, economic, and social factors. So now let's move to how to implement this in SRTI. So now we understood how to represent this as a set of simulators. But now let's look at each stage, how it is modeled in SRTI. So as you can see, here is stage 0, where we have the scenario simulator, the visualization simulator, and it's only one step. So the number of steps of this stage is 1. Here, this is stage 1, which is the disasters stage. And the number of steps here is 112, representing each step during the ground motion. And then we have stage 2, which is the losses stage. It is only one step stage. And then we have stage 3, which is the recovery stage. And this is the number of steps here is from the earthquake until the full recovery of the community. So here is an example of how to run the simulators with SRTI. So most of the simulators are modeled in, or all of them are modeled in MATLAB, instead of the visualization simulator, which is modeled in NetLogo. So I'm not sure if you can hear the voice over the video or not. So can anyone let me know if you hear the voice if I ran the video?
We don't see the video at our end.
You don't see the video? So it is the files on the screen.
Oh, okay, I see. I got it.
I'm not hearing voiceover.
So you're not hearing the voiceover, right?
No audio.
Okay. Cheers.
I thought I did when you first started.
I'd like to show an example.
There.
Okay, now you can hear it, right? I should.
Yep.
Okay. So I leave you with the video how to open SRTI and run it.
Of using SRTI to connect models or simulators from different backgrounds with different time scales, and also written in different programming languages to evaluate the seismic resilience of communities. So as you can see, here is the simulation directory. We have 2 constant folders in any simulation using SRTI, which are the GUI and server folders. The other folders in the directory represent our simulators. So for example, this is the folder related to the building damage simulator. If we open this folder, we will see the MATLAB build damage object file that contains the variables and functions related to this simulator. These three configuration files are generated automatically in SRTI, while this is the Java server file, and all the other files in the directory are related to the simulator itself. So to open our simulation, I'm going first to open the GUI file, then press File, Open, and I am going to choose the .project file that I have generated and connected before. As you can see, we have our simulators here, and the channels of the messages are here. The arrows going from the simulators represent the published messages, while the arrows going into the simulators represent the subscribed messages. So to start our simulation, I'm going to press first the power button here to allow SRTI to open each simulator in the framework. So as you can see, first the server opens, then the 14 simulators we have open one by one. So this is the visualization simulator. It's a NetLogo model that represents the power network in the community. And these MATLAB windows are for the other simulators in the framework. We have 13 MATLAB simulators with 13 MATLAB windows and one NetLogo simulator. So as you can see in the server GUI, we have 16 connected simulators representing our 14 simulators plus the GUI and the servers. So to start running our simulators, I'm going to press the play button here. So you can see here the busy simulators are highlighted in red, while the idle simulators are highlighted in blue. So as you can see here, we have our simulators first in stage 0. The scenario simulator is now publishing all the information about Shelby County to all the other simulators in the framework. So it takes some time for the scenario simulator to send the message, because the message is very long, because it represents different variables with the size of 290K buildings. So as you can see now, we have moved to stage number 1, which is the earthquake itself. And again, the red simulators are the simulators that are busy. So as you can see, the message is going from the hazard simulator, then the damage, then the performance, then the visualization. So to see the visualization side by side with our GUI, I'm going to have the GUI here and the visualization simulator here. So in the visualization simulator, we can see a plan for the power network in Shelby County. So the blue nodes represent the nodes that are not damaged, and here we can see the overall connectivity of the network. So this visualization simulator is updated in real time with the GUI or the damage simulator in the GUI here, so we can see real-time damage of the power networks during the earthquake. So for here, I'm going to pause the video, then I'll return back when we reach the damage of the network. So as you can see here, damage has started to happen to the different nodes in the network. So as you can see here, the green color nodes are the nodes in the slight damage state, while the yellow are the moderate. So as the time goes, these damage states change during the earthquake. So here you can see we started with, to see orange damage states, which are extensive damage states. And you can see here we have a drop in the connectivity of the network, so we can see this information in real time. So as you can see here, we reached the big ground acceleration of the ground motion. So as you can see, the drop is large in the connectivity, and here we can see the location of each damage in the power network. So as you can see here, we have reached the end of stage number 1, which is the earthquake stage, and now the simulators are moving to stage number 2. So as you can see here, the simulators are all blue, and here we can see the simulators in stage number 2 are turning to red, which means that they are busy calculating the earthquake losses after the seismic event. So now we have reached the last stage, which is the recovery stage. So as you can see here, we can visualize the nodes of the bar network returning back to the blue condition, which is the 100% functionality, and we can see the connectivity returning back to 1 or 100% connectivity, and we can see again the simulators turning from red to blue, and so on. So this is the example that I wanted to show of using SRTI in real natural disaster simulation.
Okay, so now let's move to the results that we can get from this for the building. So we saw the results that we can get for power networks, which has a visualization simulators showing real-time damage and recovery. So here is the damage states of the buildings in Shelby County, the special distribution of the damage, and also the number of buildings in each damage states. We can also see the building repair costs, the building repair times. All of these are the outputs of each simulator, and we can also see the household decisions. So the green parts are just repair, do the repairs. Blue part, they are decide to rebuild, and just the red part decide to abandon the community. And we can see adding the power network actually affects the abandoned household decision by increasing it. So we can also see the effect of the interdependency by adding new simulators to the system. So here is something that we did not do in our project. We did it in a different project, but we were imagining chaining it with SRTI, which is visualization of the natural disasters in virtual reality. So as we can see here, this is actually, you can see it inside the VR headset, where you can see the collapse of a building under an earthquake, this is actually based on a physics-based model, and it's converted to a virtual reality game, and you can fly through the community, see the debris effect. You can move inside the community to see the effect of the earthquake. You can feel the buildings shaking. So SRTI can allow us to see this in real time based on computed real case damage and actually recovery. So as to summarize what I presented today, so I presented the work on Semper runtime infrastructure. It's open source and free to use. It permits distributed simulation across multiple machines, or you can run it on the same machine. It supports different programming languages and operating systems. As we saw, we connected simulator visualization simulator made in NetLogo with another simulators made in MATLAB, and also we can do C++, we can do Java, and we can run this on Linux, we can run this on Windows or Mac. It also uses a publish-subscribe data transmission pattern. It uses a pre-compiled component. It achieves extensibility and scalability, and actually it does an incremental analysis in Euler sense, where each step depends on the previous one, and then it's updated based on, so it's a non-linear analysis time, not a linear analysis. So with this, I'd like to thank you all for your attendance, and I'm open to any questions.
Thank you for your presentation. Are there questions from the audience? You're also free to enter your question in the chat, and I can take a look and read it to the speaker. While we are waiting for questions, let me ask one. So I was trying to understand your framework, and you talked about the different stages, and I think stage 2 probably had a large number of steps. So. Yep. My question is, how do you typically decide the number of steps and the transition from one stage to the other?
So, for example, it depends on the hazard. So step 0 and step 2, which is the third step, are just one step. So these are outside what we have. The second step, which is the hazard step, it depends on the input hazard. So for example, if we have a hurricane that lasts for 3 hours, and we have the wind speed at each minute or 3 minutes interval, then in the hazard simulator, we can measure the size of the array we have for the wind speeds, and the size of this array is the number of steps. So, or you can define and tell SRTI to skip one step, and like it's a for loop. So in SRTI, you can define the number of steps, or you can make it defined from the scenario simulator. You can also define which frequency you need SRTI to run, each step, each 2 steps, each 3 steps, and so on.
Okay, thank you. So if my understanding is correct, then would it be fair to say that the state transition happens when the predefined number of steps are kind of exhausted? It's yep. Not like an event-based transition, so some event-based transition from one stage to the other.
Yes, it's predefined, but it's based on the event. So you can, again, make it defined through the simulation. So, for example, the scenario simulator will send a message, I finished. Then SRTI will know that done with this simulator. So when you define which simulator that controls the steps. And that's actually the management side of it. So in version 1, the user had to hard code everything. But for version 2, we had a management simulator that manages everything which is inside the SRTI. So it can be automatic, or it can be predefined by the user.
Okay, thank you. Also, I'll add another question. So why did you specifically choose Shelby County of Tennessee?
So actually, because this is the most studied, there is no specific reason for it, but this is the most studied case study, and we have a lot of data available on Shelby County. So
yeah, it was interesting because we actually had another speaker who presented, I believe, last year on results on Shelby County. So
yeah, but now actually more test beds are available. So some in California, some in Salt Lake. So now after the NSI, the National Structure Inventory data is available, I think late last year. So they provide all the data about all the buildings in the US. So you can choose whatever county you want, and then you have the data about it. Before, it was hard to get information about the buildings in the community.
Okay, thank you. We do have a question in the chat from one of our faculty members. Zelalem, let me see. So what is the main advantage of a software-based simulator of yours as compared to the physical simulator, for example, SRTI and BIS Cafe of the Pacific Northwest National Laboratory in Richland, Washington?
I would assume that the question is comparing software simulations versus hybrid or physical simulation. Is that I understand correct, the question? If so, then the main advantage will be the cost. So the for you can run a whole community, but we cannot do the same thing in the physical component. So we can do this in the software-based component. We can run, as we saw, on a whole county, considering all the interdependencies, although the accuracy or the validation is a little bit hard, which is the case for any resilience or natural disaster framework where you cannot validate it, where the physical simulator. So there are advantages and disadvantages. The advantages are related to the scalability. The scalability, you can scale it up, but the disadvantages related to the validation. So,
okay, Zelalem, if you have further questions on that or any comments, feel free to let us know.
Thank you. I was worried about the accuracy, so he just mentioned it. So we are talking about earthquake disasters, so the accuracy matters a lot. So the physical simulators usually, especially when we talk about the Cascadian anticipated earthquake, 9.5 magnitude. So that's why I just really want to know, but he mentioned it. So thank you very much.
Mm-hmm. Thank you. Thank you for the question.
Thank you. So on those lines, so all of the different simulators that you kind of mentioned in the SRTI framework, what would you say would be kind of the limitations on what can be accommodated by the current SRTI version 2?
I would say the speed of the simulations. So when you go to a larger community or a larger detail of the simulator. So again, the building damage now is just a fragility curve. You generate a random number, get the damage or get the probability. But if you would like to have an open season model, for example, then the simulation time will be large. And then, of course, sending and subscribing the message will take also more time. That's the first limitation, which is related to the simulator itself. Another limitation is related to SRTI, which is the size of the message. So the size of the message largely affects the behavior of SRTI. So for example, if we are passing just the building damage for 100,000 building, then the JSON message will be shorter than if we did it for 500,000. So sending a 500,000 building message will actually lead to significantly higher time in sending and just sending and receiving the message. So these are the two limitations that we have right now.
Thank you for your answer. Are there other questions from the audience?
Hello, Dr. Omar.
Hello.
So I have a question, like we have to build our own simulations in order to plug them into the SRTI, right? So the wrappers that we use are specific to the languages of the simulators that we use, and those can be used to extract the variables that we use in the simulator. So can we use like a general structure for a simulator in order to build something, and we can just change the variables in order to achieve different things?
That's actually a good question. So again, the wrapper actually is in version 2, which is I mentioned it's more when it's trained than version 1. So what you mentioned can be done in version 1, but the user has, again, it's for expert users. And actually, by the way, both versions are available. Version 1, you need to do what you mentioned. You need to define the variables and tell SRTI what to do. But the wrappers, as you mentioned, are available for certain languages. So it's available only for C++, Java, and NetLogo, and MATLAB. So for example, if you are using Python, for example, then you need to import the library API and then use them in Python to define your messages. So that's the difference, main difference between version 1 and version 2. I hope this answered your question.
Okay, yeah, got it. Thank you so much.
Other questions for our speaker? Okay, I will ask one last question. So, what does the research look like for SRTI, like version 3 and so on?
Actually, now it stopped because we graduated and the project ended. So now no one is working on developing it, but it's open source. Anyone can grab it and develop what they want. It's available in GitHub, and also the documentation of it is available. And the contact of the person who developed it is available as well. But now there is no current progress on it.
Okay, thank you.
I had a question about if there were existing that you knew of combined simulations that we could see that are strongly like from social data included with hazard data. Does that make sense? Like not necessarily housing and economy, but community level connective, network kind of social network data, if you knew of any people employing SRTI kind of at that level.
To my knowledge, no. Actually, I don't know if it's available. But what we did here is we tried to combine actually the household decision, which is done by the social team, our engineering part, which is related to engineering team. So we did it internally between our group, but we did not do it externally with other groups. So.
Thank you. So if there are no other questions, I would like to take the opportunity to thank our speaker for presenting the SRTI to track and the overall WC community. Thank you so much.
Thank you. Thank you. I appreciate it. Thank you.
Okay. So with that, I will say all of you have a good day. Thank you all for your attendance for the seminar. And I hope I will see you in future seminars.
Thank you.
Okay. And take care. You have a good day.
Bye-bye.